So let's discuss about the seismic design, the vibrations that define our safety. This is one discussion, group discussion. So everyone, today we are diving into one of the most fundamental concepts of earthquake engineering. That's nothing but vibration. But before we get into the nuts and bolts, let me ask you something. Let me ask you all something. Why is it so important to understand how the buildings vibrate during an earthquake? Engineer 2 is telling that we need to understand this because the vibration is what ultimately determines how a building survives or fails during an earthquake. If we don't grasp the patterns of vibration, we can't design the buildings that can withstand forces of nature. So let's break it down. Exactly. So we can break this down into three key questions. Can anyone guess what they are? I think it's something like, how does that building vibrate? How fast does it vibrate, and how much the building vibrates? Spot on and on. Those three questions are the heart of the seismic design. So what are those three questions? How does the building vibrate? How fast? So how does and how fast it vibrates, and how much of the mass or how much of the building vibrates? So these three questions are heart of the seismic design. So let's take each one step by step. So first, how does it vibrate? What does that mean to you all? Looking at the 3D model screen, that's all about the model shape. Think of it, it's like when you plug a guitar of a string, it vibrates in a particular pattern, right? The building does something similar when it shakes, except instead of string, it's a whole structure. Each part of it moves in a different way depending on the mode of vibration. The modal shape is essentially the pattern in which the structure naturally vibrates. Does that make sense? So the building has different vibration patterns, almost like different ways it could move. Different patterns means almost it has different ways it could move. Exactly. If we could frame the building while it's vibrating in one of these patterns, we'd see it deflecting in a very specific way, like a wave moving through it. Each of those deflections is what we call a mode shape. So I understand, like, what are the mode shapes? Like if we could freeze the frame, the building while it's vibrating one of its patterns, we'd see it deflecting in a very specific way, like a wave moving through it. So each of those deflections is what we call as a mode shape. So and when the structure vibrates, it's not just one shape doing the work. It's not just the one shape it's doing the work. We often get a combination of multiple modes happening at once. So it's a combination of multiple happens that's happening simultaneously at once. So while the first mode is most obvious, the higher modes can come into play too. So first mode we can see it most obviously, the higher modes can come into play too, right? So if a building is subject to an earthquake, it might vibrate in several different ways simultaneously. So it will vibrate in several different ways simultaneously, but the first mode is usually the most important one. So first mode is the most important one. Now let's move to the next question, like how far does it vibrate? How fast does it vibrate? How fast? That's where the modal period comes in. Like, can anyone explain what the modal period and why it matters? Can anyone explain what the modal period is and why does it matter? Like, does it have something to do with the time it takes for the building to complete one vibration? Exactly, like it's going to deal with how much time it takes for the building to complete one vibration. Yes, exactly. The modal period is the time it takes for the building to go through one complete oscillation in given mode. So it's clear, right? Like the modal period is nothing but the time it takes for the building to go through one complete oscillation in a given mode. The longer this period, slower the vibration. It means like if it takes a lot of time, then it moves very slowly, right? So if you are moving very slowly, means like you will take a lot of time to complete one cycle, like some complete displacement, right? That's why it's also the longer this period, slower the vibration. And you will notice that first mode of vibration, that's the fundamental mode, is the slowest. So always you can see that fundamental mode is the slowest. That means it takes more time. So natural period will be more for the first modal period. So it means like it moves very slowest way. But as we go to the higher modes, they tend to vibrate much faster. These higher modes are shorter in their period. So it vibrates fastly, so its period is shorter. And that's why the earthquake prone areas, we need to consider not just how a building moves, but how fast it can move. So it's not like how it moves, how fast it moves also we need to consider. A building vibrating too fast in higher modes might cause damage to certain structural elements, even if the shaking is not that intense. Even if it's not that intense, right? Great point. So faster vibration in higher modes can be just as dangerous as the slow ones, depending upon the building design. Now for the final question, how much mass is involved in the vibration? So how much mass is involved in the vibration? This is where we talk about the modal mass. It's the amount of the building mass that participates in the vibration of a given mode. So for a particular mode, how much amount of the building mass is participating for that vibration? Not all parts of the building are equally affected by every mode. So one thing we have to understand, like for each and every mode, not all parts of the building are affected. For example, higher modes, certain floors or structural elements may not deflect at all. So some of the higher modes, some of the part of the building does not deflect at all. So in the first mode, every part of the building moves together, but in higher modes, certain areas don't move as much. So it's clear, like in the first mode, every part of the building moves together, but in the higher modes, certain areas do not move as much. Exactly, in the first mode, the entire mass of the building is generally involved in the vibration. So we can understand like why the first mode is very important, like because in the first mode, entire mass of the building is generally involved in the vibration. So the higher modes may involve less mass. Certain floors might hardly move, but it's essential to know how much mass is involved in each mode. So we can understand like how much mass is involved in each mode, because that's how we predict the structure's overall response to an earthquake. So we need to predict the overall experience, overall response of the structure. Means we need to understand like each mode how much mass is getting participated. So here's the kicker: modal mass doesn't just affect how the building moves, it affects how much force the building can withstand. So modal mass, how much force it can withstand. The more the mass in the mode, the more force it can carry. That you can understand the one more thing also. If the more mass is participating, means like more mass is moving together, means then more force it can carry, right? So that's where the lateral force, seismic force important. Means first few modes we need to consider effectively, because more mass is participating, more force is coming into play. So to recap, we have three main properties: modal shape, how the building vibrates. That's the modal shape. Modal shape deals with how the building vibrates. Modal period, it deals with how fast it vibrates. And modal mass, how much mass participates in the vibration, or how much part of the building is participating in the vibration. And all of these properties are determined through something called modal analysis. So how do we calculate all these, how do we find out all these properties? Means we have to do the modal analysis. This is a process where we calculate the vibration patterns of the structure, its natural period, and how much mass moves, how the masses move. Once we understand these properties, we can design the buildings that not only stand up the force of an earthquake, but can also be tuned to vibrate in ways that minimize the damage. If done correctly, it's the difference between the building that crumbles in an earthquake and that's the one stands firm, saving lives and protecting property. So now this building is a real life example of everything we just discussed. Every beam, every floor was designed with understanding of these modal properties. The modal shapes, modal periods, and modal masses all play a crucial role in how we designed the building to resist earthquakes. That's the key. We don't just throw together a building and hope it survives. We study the vibration patterns in detail to make sure this building responds in the safest way possible when earth shakes. So we study the vibration patterns in every detail to make sure the building responds in the safest way when the earthquake happens, when the earth shakes. Imagine if we didn't consider these dynamic properties, a building might vibrate too fast or in the wrong way, causing catastrophic damage or failure. So I understand, like if you don't study all these details, if you don't properly understand these dynamic properties, or if you don't consider these properties, the building can vibrate chaotically. It can move fast here and there. It can cause a lot of damage to the structural components. It can cause catastrophic failure. So we need to understand all these things, and we need to study these dynamic properties properly. We need to account all these factors. And that's why the modal analysis is more important, more than just an engineering tool. It's a lifesaver. So it's a lifesaver. When the ground shakes, that's what gives us confidence that this skyscraper will withstand strong no matter the force of nature. So this whole process, it's just about making the building stand. It's about making sure it vibrates in the safest way possible. We need to make sure the building vibrates in the safest way possible. Exactly, it's all about understanding the movement, how the building moves, how fast it moves, how much mass moves with it. And once we know that, we design with precision. So how it moves, how fast it moves, how much mass, how fast, how much mass. These are the key things. That's it.